This is the first video of a short series of lectures on economic modeling for strategic management. We are going to cover a few influential papers in economics and strategy that had impact in the fields, but also that provides tools that are flexible enough to be used in a variety of different applications. The idea is not really to provide the knowledge required to write a full 40 pages applied theory paper, but more to provide modeling skills and tools that can be useful if someone wants to develop a short theory section in an empirical paper. A simple microeconomic model to think about the key economic trade-offs, to think about the data generating process, to develop additional prediction to test empirically. The material is taken from a PhD course that I've been teaching at the University of Toronto for the past few years. This is a PhD course in strategic management. Not necessarily the students have a background in economics, so some basic knowledge of microeconomics, game theory, and calculus is required to follow the material, but not really some graduate level economics. The first paper that we're going to examine is the paper by Aghion and Tirole titled The Management of Innovation. It's published in the Quarterly Journal of Economics in 1994. This is a paper that studies the organization of innovation activity in an incomplete contract setting. There are a lot of results in the paper, but the one that we're going to focus on in this video is essentially whether or not a firm should have its own research and development unit, should own a research and development unit, or it should interact with an external unit to develop new technologies. One key idea in the paper is that research and development is a special activity, is different from other type of economic activity because it's difficult to describe. It's very hard or even impossible to list all the tasks that are required to develop a new technology. And this difficulty in contracting over R&D may lead to very big differences in the likelihood that a technology is developed and in the profit that can be made in a technology in the case in which a research unit is owned by a company compared to the case in which a company interacts with an external research unit. And the paper identifies condition under which it makes more sense for a firm to own its R&D unit, and it makes more sense instead to interact with an independent entity. This paper is an important contribution to the field of economics of innovation and management of technology, but also the model that is developed here is a fairly general model that has the potential to be used in all sorts of other applications in strategy. There are a lot of other settings that someone can study in which two or multiple parties have to invest together in a strategic environment. There are some problems in really use contracts that specify precisely these investments. And the one wants to compare whether or not the allocation of property rights or the boundaries of the firm may affect the interaction between these entities. So this is a natural model to study this type of problems and settings. So I'm going to start now with the mathematical examination of the model using a notepad, essentially in the same way that I would use a blackboard in class. Okay, this is a simplified version of a classic paper in the economics of innovation. It's by Aghion and Tirole, and it's published in the QJE in 1994, and it's called The Management of Innovation. In this model, there are two key players. The first player is a research unit that we indicate with the letter capital R. And the second player is a customer that we indicate with the letter capital C. The idea is that these two players have to develop a technology, and they develop the technology together in a sense that it require effort, research effort, both by the research unit and by the customer. Okay? We indicate the effort of the research unit by little e, and the effort by the customer by capital E. And the probability that a technology is developed successfully depends on the two efforts, and we call this probability little p of E capital E. Okay? So this is the probability that a technology is developed given the effort of a research unit and the effort of the customer. If the technology is developed, the value of the technology is indicated with capital V. So capital V is the value of the technology. So this is the basic structure of the model, essentially the key parts of the model. And what the paper does is essentially to compare two big cases. The cases of non-integration. It is the case in which R and C are two different entities and they negotiate to split V if V is developed successfully. In the case of integration, which is the case in which R is essentially owned by C, okay? They're not independent, but R is owned by C. Now, in the case of non-integration, the assumption is that the value is divided equally between the two players. Each gets V divided by 2. In the case of integration, the assumption is that the customer gets the full V and the research unit gets nothing. So these are like a very strong assumption on the payoffs in case of successful development, and there is a discussion in the paper on how this assumption can be relaxed. But what is crucial here is that these are incomplete contracts. In the sense, it's not possible to have splits of values that depend on the effort, in particular on the effort of the research unit. Cannot say in this particular case, okay, research unit, you're getting a particular amount of V if your value of little e is equal to a particular target. That cannot be done. In particular, this effort is non-contractible, contracts are incomplete. And this generates a number of interesting results in the model. Now, the probability of developing a technology that is indicated with P, little e, capital E, is assumed in the paper to satisfy a number of properties. The probability of discovery has to be increasing and strictly concave in little e and capital E, and has to be separable. Separable means that P of little e capital E can be written as the sum of QE plus R capital E. It's separable in the sense it can be written as the sum of these two functions that only depends on one of the two parameters. Now, the model then works using these general forms of P written as the sum of Q and R. And this can be something challenging to follow for someone like a master's student or a first-year PhD student. I definitely remember when I was in graduate school, it was not easy to follow modeling that was working with functions that were too general. So here my suggestion and the approach that I'm going to use in this video is not to use this general formula, but to find an example of a formula that satisfies this property, and then solve the model with this example. This makes it much easier to follow and obtain the results. And it's also something that is actually done in practice. When you do apply theory, very often you start developing insights and some results with some specific example of a functional form, and then you try to understand how general this result is. Okay, you rarely start with a very general functional form. You start with some example to develop the intuition. So in this particular case, what I suggest as a function to use that satisfies this property is the following: P of little e capital E is equal to 2a square root of E divided by theta plus 1 minus a square root of capital E divided by theta, where a is a parameter between 0 and 1, and theta is a large number. Why I write a function like this? So as you can see, first of all, it is increasing in E and in capital E. It's concave because it's increasing with the square root, that is a concave function. I have the 2. The 2 here are useful because if we have to take derivatives, derivative of the square root gives you a 1/2 that goes around the formulas, and with the 2 you can simplify and get rid of that essentially. Theta, I want to divide everything by a large number because this is a probability. It cannot be greater than 1. So if I assume that everything is divided by a large number, that means that it's always below 1, so it's a probability. And a is a parameter that I introduced. I could have done without it, but it's a nice parameter that helps us understanding how is that result change if I increase the importance of the effort of the research unit and the effort of the customer. So as you can see, if a is equal to 1, only the effort of the research unit, little e, matters. If a is equal to 0, only the effort of the customer matters. And if a is equal to half, they matter in the same way. So it's a way to kind of consider cases in which the efforts of the two players have different importance, and one is more relevant than the other for the development of the technology. Okay, the next thing we're going to look at is what is called the first best. So the maximum welfare that can be generated in this model. So first of all, let's try to understand what is the welfare here that can be created if the research unit invests little e and the customers invest capital E. Well, we know with the probability P little e capital E a technology is developed. In that case, the value created is equal to V. But efforts E and capital E are also costly. And in the model, the assumption is that it costs exactly 1 unit of effort. Essentially, the cost is linear. So the cost of 1 unit of little e or 1 unit of capital E is equal to 1. So as you can see, this is the surplus that you create with specific value of investment little e and capital E. And the first best is obtained if we maximize this respect to E and E. So you want to find essentially the value of E and E that maximize the surplus. Now let's use the the functional form that I suggested before. So we have 2a square root of e divided by theta plus 2 1 minus a square root of capital E divided by theta times v minus little e minus capital E is the function to maximize. And to maximize, for example, respect to little e, I have to take the derivative of this respect to little e, right? And set it equal to 0. So in this case, if I take the derivative of this and I set it equal to 0, I have 2a, the derivative of square root of e, that is half e negative half divided by theta times v minus 1 equal to 0. Okay, see, this is the derivative of the square root of e, and this is the derivative of e. All the others, terms don't depend on e, so this is equal to 0. And now I can solve for e. Solving becomes easier because this half simplified with the 2. This is why I had that half there. And it can be rewritten as av divided by theta is equal to square root of e. That solving for here give me e star. This is the e that maximizes the surplus, so the first best e, that is equal to a square v square divided by theta square. I can do the same thing, okay, here with capital E instead of e. So I take this derivative of this function here respect to capital E rather than little e and set it equal to 0. And I can obtain the first best value of capital E that is very similar. The only difference is that instead of having a here, I have 1 minus a square v square divided by theta square. Okay? So these are the first best level of efforts, little e and capital E. So now that we have obtained the values of little e star and capital E star that maximize the welfare, we can actually compute the maximum welfare that can be obtained. And this is obtained by replacing this value of little e and capital E star in the welfare function. So we have essentially 2a square root of little e star divided by theta plus 2 1 minus a square root of capital E star divided by theta that multiplies v minus e star minus capital E star. Now replacing this with their values, we have 2a square root of E star is equal to av divided by theta plus 2 times 1 minus a square root of capital E star, that is 1 minus a v divided by theta, everything divided by theta, right? That multiplies v minus E star, that is a square v square divided by theta minus capital E star, that is 1 minus a square v square divided by theta square. Also here there is a theta square. Now as you can see here, there is a lot to simplify. This can be rewritten as 2a star v square, 2a square v square divided by theta square plus 2 1 minus a square v square divided by theta square minus a square v square divided by theta square minus 1 minus a square v square divided by theta square. That gives v square divided by theta square that multiplies a square plus 1 minus a square. So this is the formula essentially of the total welfare at the first best, the maximum welfare that can be generated in this model, and it's something that we're going to use later to compare with the welfare generated in case of integration and non-integration. Okay, now that we have solved for the first best, we're going to look at the case of integration. Remember, in the integration case, the research unit received no reward for innovation. So in this particular case, we should expect no effort by the research unit. So little e equal to 0. And this implies that the profit made by the research unit, we call it capital U-R-U, is also equal to 0. Okay? I exert no effort and I get no reward, so in total I'm going to get 0. Things are different for the customer. The customer now owns the technology and you get full V if it's developed, but it is developed with no effort from the research unit. So the utility of the customer is going to be equal to the probability of developing the technology given that the research unit makes 0 effort times V if the technology is developed minus capital E, that is the effort of the customer. So the customer maximizes this respect to E, okay? And it takes the derivative and set it equal to 0. If I use the functional form that I had before, I have that P of 0E is equal to 1 minus A 2 square root of capital E divided by theta, and therefore the derivative of UC respect to capital E is equal to 1 minus A times 2 times half capital E with the exponent negative half divided by theta times V minus 1, and this is to be set equal to 0. And this gives me that the optimal E is equal to V squared times 1 minus A squared divided by theta, that is exactly equal to the first best E. Okay, so let me push it up so that it's more easy to read. And the result here shows essentially that the effort of the customer doesn't change, is exactly equal to the first best level, and this is come from the separability of the assumption of the formula of the probabilities. But what is very important here is that with integration with the customer owning the RU, there is a big difference in the efforts of the two, with the effort of the research unit going to be very low relative to the first best compared to the effort of the customer that remains closer to the first best. Now we said that the utility of the research unit is going to be equal to 0. The utility of the customers is not equal to 0, is equal to P0 E star now times V minus E star, that is equal to, if you replace this E star with this one, is equal to 1 minus A square v square divided by theta square. Okay, so this is the utility of the customer in the case of integration. We now move to the case of non-integration. The case of non-integration, both the research unit and the customer get half of V. So if I want to be specific, the utility of the research unit in the case of non-integration, and we follow the notation of the model, we call the utility U with the wiggle, is equal to P times P that depends on little e and capital E times V divided by 2 minus little e, and the utility of the customer is equal to P also that depends on the two efforts times V divided by 2 minus capital E. Here, if I want to use the functional form that we use in our example, for example, for our U, we have that this is equal to 2a square root of little e divided by theta plus 1 minus a square root of capital E divided by theta times V divided by 2 minus little e. Now, in a sense, this becomes now a game. It becomes a game in the sense that the research unit chooses E to maximize its profit, and the customer chooses capital E to maximize its profit. In principle, the payoff is a game because the payoff of the research unit depends on the effort of both firms, and the payoff of the customers also depends on the efforts of both firms. The fact that there is separability actually facilitates the things. Let me solve for the optimal effort of the research unit. This is obtained by taking the derivative of the utility of the research unit with respect to little e and setting it equal to 0. The derivative here is equal to 2a e with exponent negative half times half divided by theta times v divided by 2 minus 1 equal to 0. So as you can say, it's a game, but because of the separability, once I take the derivative, essentially it becomes only function of little e. And if I solve here for the optimal value of little e, and I call it little e wiggle, this is equal to v square, a square, divided by 4 theta square. If I do the same thing for c, I take the derivative of u c wiggle with respect to capital E, and I set it equal to 0, then I obtain the optimal effort of the customer with non-integration, that is equal to v square 1 minus a square divided by 4 theta square. And the idea here, what you want to see is that it's different, the case of non-integration compared to the case of integration in terms of efforts. In terms of integration, with integration we had no effort from the research unit. Now we have some efforts, and we also had effort from the customers. We also have effort from the customer, but now it's smaller. It's divided here by 4. Before it was not divided by 4. So the idea is that it increases, compared to non-integration, the effort of the research unit, but it reduces the effort of the customer. This is the effect that we have comparing integration with non-integration. Okay, we have obtained the efforts in the case of non-integration for the research unit and the customer. The next thing that we need to do in order to obtain one of the most important results is the paper, is to compute the utility or the profit of the customer in the case of non-integration. This is equal to the probability of developing the technology, that is equal to 2a square root of E wiggle divided by theta plus 1 minus a and square root of capital E wiggle divided by theta times v divided by 2 minus E wiggle. That is essentially the payoff computed with the efforts that you have in equilibrium in the case of non-integration. So now if I replace E wiggle with this formula and capital E wiggle with this formula, I obtain that this is equal to 2 a square root of v square a square divided by 4 theta square divided by theta plus 1 minus a square root of v square 1 minus a square divided by 4 theta square divided by theta, all this multiplying v divided by 2 minus v square 1 minus a square divided by 4 theta square. This is equal to, if I simplify this, to a square v square divided by 2 theta square plus 1 minus a square times v square divided by 2 theta square minus v square 1 minus a square divided by 4 theta square. That give me the final result, the final formula, that is a square v square divided by 2 theta square plus 1 minus a square v square divided by 4 theta square. Okay, this is the formula of the utility of the customer with non-integration. Okay, what we are going to do now is to compare the utility of the customer in the case of ownership of the research unit and in the case of non-integration, to understand whether it's better for the customer to actually own or not the research unit. And we're going to find a situation in which actually not owning the research unit is better, okay? Non-integration is preferable. So remember that we found that UC was equal to V squared times 1 minus A square divided by theta square. And we also found that UC wiggle was equal to A square V square divided by 2 theta square plus 1 minus A square V square divided by 4 theta square. So the difference now between UC wiggle and UC can be written as a square v square divided by 2 theta square minus 3/4 of 1 minus a square v square divided by theta square, which can be written as v square divided by 4 theta square that multiplies 2a square minus 3 1 minus a square. This part here is positive because it's all a square, so this is positive or negative depending on whether this term here, 2a square, is greater or not than 3 1 minus a square. Okay, is greater or negative than that. Let's try to understand conditions under which UC wiggle minus UC is positive. So the customer is actually better off without integration. This takes place if 2a square is greater than 3 times 1 minus a square. That can be rewritten as a square minus 6a plus 3 has to be strictly less than 0. Okay? And this is satisfied only if a is large enough. A has to be greater than 0.55. Okay, so if you solve for this, you see that when a is equal to 0, this is equal to 3, so this is not satisfied. But as a gets larger and toward 1, this becomes negative. Okay, for example, when a is equal to 1, this is equal to 1 minus 6 plus 3, that is negative 2. So a has to be large enough. A has to be greater specifically of 0.55 to have that the utility of the customers from non-integration is greater than the utility of the customer with integration. And this is essentially one of the first results of the paper. It's discussed in the first proposition of the paper that essentially says that it makes sense to allocate property rights to the research unit, so to have the research unit independent, when the marginal efficiency of its effort is large enough relative to that of the customer. Okay, and if you remember A in the formula for the probability of development, right? A was in fact the effect of the effort, was capturing the effect of the effort of the research unit relative to the effort of the customer. Okay, so this is essentially the first result. It is not always necessarily the case that as a customer you want to own your own research unit. If by owning the research unit, the investment of the researcher are going to be lower because you cannot compensate them enough, okay? You can be better off by interacting with an independent unit. You're going to appropriate less value in case in which the technology is developed, but the independent unit will exert much more effort, and this greater effort increases the probability of developing the technology, and this makes you better off. Okay, so this is essentially an interesting insight on when is that you want to have big boundaries of the firm and to have a research unit owned by a customer, or you don't want to have a large boundary and you want to have two independent firms. By giving independence, essentially, you compensate for the fact that contracts are incomplete, and you induce more effort from the perspective of the research unit. Okay, the next thing we're going to look at is to consider the case of change, essentially, between integration and non-integration. Will this happen? If this is, and under what condition a party will give up property rights. So let's consider the case of non-integration. Let's assume that the owner of the research unit can make an offer to the customers and say, look, I'm going to sell RU for capital T dollars. Okay? Will the customer accept that or not? And does it make sense for the research unit to be sold at T dollars? Well, the customer will buy the research unit for T dollar only if the utility that the customer does with integration, this UC, minus the T dollars that are paid, exceeds the utility without integration, that is U tilde C. Now, it means that T cannot exceed UC minus UC wiggle. Okay, T cannot exceed this. This is the maximum T that I can charge as a research unit to sell the company, is the difference between UC and UC wiggle. And actually, we're going to follow here a standard assumption in bargaining theory. It is that if the unit as the bargaining power makes the offer will be exactly equal to the maximum that I can extract. So if I can have option, you can ask all sorts of amount of money to have my offer accepted. I'm better off asking for the maximum amount of money that is going to be accepted. So the T is the difference between UC and UC wiggle. Now, if I assume that T is equal to the difference between UC and UC wiggle, then does it make sense for the research unit to sell the ownership for T dollars? Well, this makes sense to the research unit if the utility that I get, UR, without ownership, plus T, that is the amount of money that I get giving up the ownership of the company, exceeds the utility that I make in the case of non-integration. Now, if I substitute T here with the formula that we just found, I get that this condition can be written as UR plus UC minus UC wiggle as to be greater or equal than UR wiggle, or UR plus UC is greater or equal than UR wiggle plus UC wiggle. Okay? What does this mean? Well, it means that the research unit is willing to give up its ownership and be integrated, give up its independence and be integrated with the customer if the sum of the utilities of the two players in the case of integration exceeds the sum of the utility of the two players in the case of independence. And this is essentially what it says in the proposition, in the second part of proposition 1, that the allocation of property rights is efficient when the research unit has the bargaining power. So that if the research unit is the one deciding whether or not to sell its independence essentially for T dollars, is making that offer, then the allocation is going to be the allocation of property right that maximizes the sum of the utility of the two, so the efficient allocation. In the case of integration, though, things are different, because here the assumption is that in the model is that the research unit has no money. The research unit cannot pay the customer to become independent. Okay, so it's just a choice of the customer, and we have seen before that the customer is going to keep ownership of the research unit as long as UC is greater than UC wiggle. We saw that in the previous result. But UC can be greater than UC wiggle even if UC plus UR is less than UC wiggle plus UR wiggle. So the sum of the utility of the two players can be greater without integration if the two units are independent, but the customer is going to keep the ownership because it cannot ask the research unit to pay to become independent. Okay, and this is essentially also the final part of the proposition 1. It says the research unit cash constraint might induce the customer to inefficiently retain ownership when the customer has the bargaining power ex ante and has to decide whether to split the company into two independent companies or not. Okay? So this is concludes essentially the analysis of the proposition 1 of the paper and shows you the key insights from the paper. And as you can see, the amount of the importance of the effort of the two players on the final probability of developing the technology is really crucial to understand whether the players are better off or not with independence. And also, you're going to reach independence when it is best for the two players to be independent, only if the party that is not cash constrained is in a situation of being able to compensate the other party. If cash constrained situation may induce to an ownership structure that is not the one that maximizes the utility of the two players.